Okay, here we are. Just 1 second. All right, so we've been talking about local bifurcations. Remember, a bifurcation is an event at which there's a local change in the topology of a system. We're talking about parameterized families of systems. And we're talking about their behavior near an equilibrium point. So when you find that the system is not topologically equivalent to all nearby members of the family, then a bifurcation takes place. Just to kind of scroll back a little bit to that, these were the ideas when we started fixing them. Again, we're talking about parameterized families like that. And the big picture is that in the space of dynamical systems, once you have a parameterized family, and remember, each dynamical system is just a point in this space, right? And a parameterized family would experience a bifurcation if it goes through essentially a dividing surface that divides different topological equivalence classes of systems, right? So this would be then a bifurcation point in the history of that system. And important, again, to recall, this is not a trajectory of the dynamical system, but it's the whole family in the space of dynamical systems, parameterized by, generally speaking, p-dimensional parameters. So this is not even necessarily a curve, but a surface in general, right? Now, you have a good model if it's prepared for all eventualities, namely, if it really indeed stays robust under the things that you thought were not important and hence you neglected, which is okay for purposes of simplification, but you want to be qualitatively correct, right? So if your simplified model has the property that even if it experiences a bifurcation, varying the parameters in the system that you'll have to open will explore all the nearby equivalence classes or the nearby different topological geometric behaviors, then your system is a good model. And when we called such an embedded family of systems, you embed your point of interest, your dynamical system of interest in a family that enough parameters. We called such an embedding of the dynamical system into a parameterized family a universal unfolding. An example was here that you're in fact at the intersection of two different bifurcation surfaces. Then in order for you to explore more than just two of them out of the two of the equivalence classes, because there's a total of 4, right? One here, one there, you would need a higher dimensional parameterization as opposed to just this one, which would only explore 2 equivalence classes, and that was universal unfolding. And now for the last important bit was, in terms of terminology, is the codimension of a bifurcation. And the codimension was the minimal number of parameters needed for a universal unfolding, right? And the higher the codimension, the more parameters you need. And that means the more degenerate you are, the more of these surfaces intersect right at your bifurcation point. So that complexity could be endlessly increased, but in realistic systems, in fact, it's the low codimension ones where not everything goes wrong at the same time and you don't have all the degeneracies of the world, but rather maybe you have 1 or 2, right? Those are the important ones. So we started paying attention to those, and the most common was the single zero eigenvalue. That's what I started covering. So these are codimension 1 bifurcation of fixed points. And this is pretty much what I'm going to cover quickly. This is a classic subject. And I think Guggenheimer-Holmes has a bit more, there's more detail on this, and also some of the codimension 2 bifurcations. We'll find a very interesting discussion on that. So what's up with the single zero eigenvalue? The assumption is you have an n-dimensional system with a p-dimensional parameter set, and we're assuming that the bifurcation takes place at mu naught equals 0. If not, then you just redefine your parameters. You can always shift the bifurcation parameter value to 0, right? So that's not a problem. And then what we assume is that there's an equilibrium at 0. And we also assume that when you check the Jacobian of the right-hand side, then you find that it has a single zero eigenvalue. In other words, the center manifold of that Jacobian will be 1-dimensional because the center subspace was 1-dimensional. And people have done their homework you know, this was something that was dealt with first, clearly in the bifurcation literature. And they have showed that on an appropriate semi-manifold, depending on parameters, if you look at the truncated normal form in order 2, which it means there's no linear terms, those you can remove successfully. Remember, that was the idea of normal forms, to apply a near identity transformation that simplifies the nonlinear dynamics in the form of a Taylor expansion and then a fixed point, to simplifies it as much as possible. And this turns out to be enough. So when you truncate the dynamics here, the normal form here, then topologically, what you get from here is what's going to happen near the origin. It's a scalar parameter mu tilde, which may or may not be a component of the original parameter vector. Okay, generally speaking, in almost any component of that would work if they are in general position, right? But it really has to be something, all right, whose variation does this rather than that. Okay, but generically that would be the case. So what's the plus minus? The plus minus, I give you a little argument that the plus minus arises from the fact that that normally you would have here a nonlinear coefficient for that nonlinear term, but you can scale it out by reparameterizing time, so that conceptually you only have one parameter left. But when you scale that out, you can only do that at the expense of making an assumption that it was either plus to begin with or minus to begin with. And I went through that time rescaling here. So in any given problem, you can actually leave that parameter there. It's not going to make any difference. It's just that people like the most simple form, right? That you can get to, so that you can really focus on the essence of the bifurcation rather than look at various cases, parameter classes, some of which lead to identical results, right? But you don't have to scale it out from there. You just compute it, and then you go ahead. You do the same type of bifurcation that I plot that I have done here. So what's happening here is that for negative, let's take the negative sign. So that's the case. Then you have a stable I'm sorry, not stable. You have no equilibrium point here for mu less than 0, because that's negative, and this is also negative. So no way this can be 0. But the things change when mu tilde is either 0 or positive. Then you have two branches. This one is stable, the other one is unstable. They open up like square root mu tilde. This is called this is called supercritical fold bifurcation. Supercritical because it happens over the critical value, which is mu equals 0. If you happen to have a plus sign here, then the whole thing repeats itself, but in this direction. So the bifurcation then takes place below the critical level, the critical bifurcation parameter, critical value of the parameter. So then it's called then a subcritical fold. And I spent some time on this one because it does happen a lot. You know, this is kind of the simplest degeneracy that can happen. And for that reason, just as I said, on probabilistic grounds, this is what you're supposed to see the most often, right? And yes, pretty much you look at experiments, they already display this, and it manifests itself, although people often miss it, it manifests itself in a hysteresis type phenomenon in which your response actually seems to depend on the history and one's first of the experiment, and the one's first inclination could be, oh, this has to be some kind of sort of complicated modeling. I have to have a memory term. I have to integrate over the past, have a functional differential equation and whatnot, right? That only accounts for the past of just the present. But that's not the case. It's really just a bifurcation diagram that you see in front of your eyes when you see this from a jump here, when you go in this direction with the parameter, and then an alternative route when you go back, because that was an unstable branch here, right? And when you connect that, it's just a nice continuous curve of fixed points, except that there was an unstable one, and I explained why you simply don't see that, right? So it's more of an observational matter. It's not some mysterious I don't remember the past type thing, right? I also mentioned that all this carries over to maps, which means discrete dynamical systems defined by iterated mappings. Everything carries over. Well, there's some slight modifications that some of the bifurcations the maps display, then continuous systems cannot. But fundamentally, this one is exhibited by maps. I talked about how that helps you when you talk about harmonically, time periodically forced nonlinear oscillators, right? So in that case, what you can do is, as a function of the frequency, plot the response amplitude, and you will get similar curves. But understand that in that case, this point here in any of these curves will be a fixed point for the Poincare map, not for the original continuous dynamical system. The original continuous dynamical system is non-autonomous, is being forced time periodically. So the reason I'm showing this picture is not as some sort of non-autonomous extension on the results, but rather I'm changing the setting. I'm passing to an autonomous time t mapping. The mapping, likewise, can have and will have center subspaces, center manifolds, and the like, right? But the critical linear behavior for the map that leads to a bifurcation is not having a 0 eigenvalue for its Jacobian, but having a 1 eigenvalue for its Jacobian, right? Because a 1 eigenvalue, if you're mapping xn, if xn is mapped to xn plus 1, that's a fixed point, right? But if you write f, y equals f of x, and you're iterating this, then since you're getting identity, you need a 1 eigenvalue there rather than a 0 eigenvalue to make that happen. So that's pretty much the only difference. And as I indicated to you, the big dividing line for where all the problematic eigenvalues that lead to bifurcations, that line, which is a line for continuous dynamical systems, the imaginary axis on the complex plane, that turns into the unit axis, unit circle of the complex plane for maps, because any eigenvalue that has 1 in norm, complex, but 1 in norm leads to kind of neutral behavior the same way as the 0 or the purely imaginary eigenvalues lead for continuous dynamical systems. That's something you can look up, but if you understand the continuous dynamical systems case, then there will be no surprises, but I don't have time to cover both. And this is very much, when you see this curve, it happens all the time, not just in solid mechanics, but in fluid mechanics, you see these types of hardening response curves. So again, what this was for different forcing amplitudes, you relive the same hysteresis, then you're loading, your forcing frequency goes up, and all of a sudden you jump, and when you do a down sweep, you seem to survive that, and you jump in the other direction back. So apparent hysteresis, again, what happens is there's an unstable branch for that time periodic orbit or fixed point for the time t map or Poincare map. And the other thing that I got started on was I assumed an additional degeneracy, which doesn't turn out to be that serious, so that it would increase the codimension of the bifurcation. This was kind of a little point for that basically is your bifurcation surface, and I'm just introducing an additional codimension 1 constraint in the space of dynamical systems. Namely, I'm only dealing with systems, I'm not considering all systems, I'm dealing with systems for which, despite the parameter variation, the origin remains a fixed point. So I'm just going to be operating within this plane, okay? And I can still just use a 1 parameter family of codimension one parameter family of unfoldings, just to explore and to get from one side to the other. So these systems preserve the origin, but other than that, they still have the Jacobian as a single 0 eigenvalue. Since for all mu values, the right-hand side must be 0 at 0 because the origin remains a fixed point, I can differentiate this with respect to mu, this identity, and set mu equals 0. The origin is already set to be 0. So I get a general result that to express the constraint that the origin remains an equilibrium point, at least locally, it doesn't have to happen for all mu values, but at least near mu, I have to require that the partial derivative of this f at mu at the origin must be 0. And the question is, under this constraint, what's the universal unfolding? This is going to be different than what I've already seen by all means, because this one doesn't satisfy that. This doesn't preserve the origin. Remember, that's exactly what's happening here, that the origin gets shifted, right? But in a system with a symmetry that for which the origin is always an equilibrium point, that's just not going to happen. For instance, the system is subject to symmetric forces, say 2 springs from both sides. I can tinker with the nonlinearities, of those springs, right? I can make them cubic, I can make them quintic, I can change their parameters, whatnot. But as long as the physics is symmetric, then there will always be an equilibrium point in the middle, right? So that's a subclass of systems relative to the more general class of dynamical systems, right? So it turns out that the universal unfolding for that is this, and the only change relative to the previous one is that now I have a linear term there. So I no longer have a constant term there, but I have a linear term, mu tilde not by itself, but multiplied by x. X is a one-dimensional variable on the parameter dependent center manifold. And then again, I have the plus minus, okay? And this is where I stopped last time. If there's any question about this, I'm happy to answer before I move on. Anything? I think conceptually this is pretty clear at this point. Yeah, but let me know if, again, I'm in constant uncertainty if the audio works, but I installed the new operating system, so I can't make any promises, but hopefully it works. But I'm keeping an eye on the chat anyway. So how do we go from here? So I just need to analyze this more specific system. It's not that complicated to analyze. The bifurcation diagram is easy to plot. So what would that be? The bifurcation diagram again is a plot of the equilibria that exist for a particular value of this parameter mu tilde, which is the unfolding parameter. Let's again pick the minus case, which used to be the subcritical. In the first, we'll see if this is any different here from that standpoint than the plus case. So let me then draw a bifurcation diagram here, to which I need again two axes. So this will be the mu tilde axis, and then this will be the x axis. Okay, and what I see is that x equals 0, because that was my assumption, remains to be an equilibrium for all values of mu tilde. I can read off its stability immediately, right? Because mu tilde is the eigenvalue if I linearize. So when mu tilde is negative, I have stability. When mu tilde is positive, I have instability. And remember, the bifurcation diagram in these enables me, at least for one-dimensional system, is basically not just the equilibria, but it's the whole dynamics, because on a line, I can just draw the whole dynamics. And for mu less than 0, what I have so far is a stable equilibrium, right? And for at x equals 0, and for mu tilde larger than 0, I have an unstable equilibrium. So accordingly, the arrows will be pointing towards this equilibrium here. And while I have criticality here, right there, what do I have right there? Well, right there, mu tilde doesn't tell me what's going on, right? Because it's 0. So I need to look at the nonlinear term, which is x squared. I picked the negative sign. So right here in this slice, I got x dot equals minus x squared. So that means that I have a fixed point here, but I'm coming down here, and also I start coming down here, if I did that correctly, because I just go through right the origin. So how is that possible? Well, because this is becoming really weak, this decay here, the closer I get, right? So it's faster here, and it's always exponential because I will have a decay exponent. But right there, I have 0 decay at the linear level. So whatever decay I get is nonlinear, so it's algebraic. So what you get here is a very weak arrow. But then that arrow starts gaining strength because all of a sudden you start getting positive exponential, well, not getting strength, but you start getting, again, I'm talking about the negative case. Actually, that can be wiped out. I thought I'm in the positive case, but no, I'm in the negative case. So what I have here is very weak. It's not robust. It's decay from the nonlinear terms, and the slightest linear growth can wipe that out, because all of a sudden I have a linear term and arbitrarily close to the origin, a linear term, which is non-degenerate, always dominates the nonlinear term. So it can turn things around completely. I'll draw that here. Maybe I draw just a couple more lines. So now I start growing, still weak, but I'm going to gain speed as I increase mu tilde. Another thing appears here that all of a sudden this factor, again, remember I'm looking at the minus sign here, for negative mu tilde, I could not solve this for an equilibrium when mu was negative, right? Well, I did. Sorry, that's not true. I just forgot, right? When mu was negative, I was also getting another equilibrium point, which is, well, I always get, sorry, I'm making it overly complicated. So this factor is just here, mu tilde minus x in the current case, right? And I need to solve that for 0 to see if I get another branch of equilibria. And from this, I get x equals mu tilde. So I do have this standard other branch right through this point. But you can work out that from here, that other branch must be, this one needs to be unstable. And if you do a linear stability analysis and also pay attention to the arrows, this part becomes stable. So this will be unstable at the 45-degree line here, the other branch. And then on the other end, it becomes stable. So what's the hallmark of this bifurcation? I'll just, what do you observe? Remember, in the fold bifurcation, you had a particular observation type, no equilibrium for a while. And then all of a sudden, you just observe one equilibrium, but it keeps growing as the square root, something in amplitude. You remember here? Here. So observationally, you would see, you know, no fixed behavior. The system would move, but that motion would weaken. At some point, you see a fixed point, and the amplitude of that fixed point, or the distance from 0 as a function of the parameter, would actually grow very rapidly. Okay, and at the same time, its domain of attraction would also grow, but it will have a domain of attraction. And when you're outside that domain of attraction, the boundary of which is marked by this red curve in one direction, right? Then you actually start picking up the behavior that you had before. So in the large, you're still mimicking this behavior, but in the small, a new type of behavior is opening up. So that's kind of what you observe in an experiment. And locally, this happens all the time here at these fold points in a real experiment. So here, if you try to imagine what you're experiencing in this case, and this is called, again, I think although you could, you know, argue as to, I mean, there's no bifurcation on one side or in the other side. So in principle, in terms of the number of branches, it's same as here as there. So I cannot say that the bifurcation happens before or after because they're very similar. So I wouldn't necessarily, you know, use that terminology here. Maybe in line with the previous ones, you could call this subcritical. And the other one you could call supercritical, but subcritical, supercritical, what? This is called actually a transcritical bifurcation. Okay. So what's the hallmark of a transcritical bifurcation? Well, the hallmark would be that, remember, the equilibrium point, the x equals 0 is always a fixed point. So that's already one thing that you make, that excludes the fold as such, right? The fold bifurcation, because you wouldn't know that. So that's already a hallmark that, well, wait a second, I have an equilibrium point, I'm changing parameters, I have to be prepared to see this, right? But because when you look at that equilibrium point, it's not moving anywhere, and it actually keeps the same stability type. Whereas there is a point after which that equilibrium point that you observe, interestingly, starts moving, even though the system is still capable of having an equilibrium right there, but you don't see that anymore, interestingly. So you keep changing parameter, nothing happens, right? Nothing happens. And then very gradually, your observation, not characteristically with a rapid amplitude growth, but rather with a linear amplitude growth as a function of the parameter, starts moving. And then say, wait a second, I thought that the origin is supposed to be a fixed point. And you are right, it remains a fixed point, but it becomes unobservable because it's unstable, right? So you're driven to this other one. The origin will still play an important role because it will then, in this context, mark the boundary of the domain of attraction. So you will experience a different behavior on the other side of the origin, okay? And also, unbeknownst to you, even when things were working quite well, and robustly, on the one side of your domain of attraction, actually it was shrinking. It's shrinking down linearly. So here, even though this is technically an equilibrium point, if you make a small perturbation, you can actually lose stability in one direction, but not the other. So this kind of asymmetry in your observations is also a hallmark of this bifurcation. This is not that actually typical in
We can't hear you. You are muted.
Thank you. Thanks. But the good news, I can hear you now. So that means that the audio problem is fixed. Thank you. So I was showing these forces and I said, you know, they are equal, but also note one more thing, that if not only are they equal, but also the force is an odd function of the location, right? Because if I switch to this, from this direction to that direction, I get the same force, but with a negative sign. So it's an odd function of the position. And that's very typical that these types of restoring forces in mechanical models, both in fluid dynamics and in solid mechanics. And for that reason, this is not so typical. You would need asymmetry breaking because this one doesn't know that. The linear part knows that because it's an odd function in the position, but the nonlinear term doesn't know that. So that's why this can be seen perhaps in systems that are not mechanical. And when I say mechanical, I mean more generally, you know, fluid mechanical, solid mechanical, whatever. You might see it in population dynamics models and elsewhere when the forces are not on. But it also then tells me, all right, so it seems like that, so this is often called sometimes exchange of stability. So let's actually be a bit more then specific in terms of looking at applications more relevant in mechanics or physics in general. And then I assume then one more thing. So not only will I assume that I have a simple zero eigenvalue, and which means plus origin remains fixed, fixed point, plus the right-hand side of the dynamical system is an odd function. Okay, so I assume all this. Because very often, if you have an odd function, then of course the origin will remain fixed. So it's more, then that's more of a consequence rather than the main assumption. This is really the main thing here. So let's see what that then imposes on the system y dot equals f y mu again. Y is n-dimensional, mu is p-dimensional. And my assumptions are that at the bifurcation value, I'm at the origin. So the origin is a fixed point, the bifurcation value. And the Jacobian is again such that it has the mildest possible degeneracy. So the dimension of the center subspace is 1, single zero eigenvalue. And then I assume whatever I have already assumed, that under changes in mu, the equilibrium point doesn't move. This was the constraint that has expressed that. And I want to maintain these assumptions. Like so. But now I want to add this additional thing that the right-hand side is odd in y. So more specifically, if I write it out, then I obtain that the fy0, at least, I'm just going to, I'm at least locally. Okay, locally mu, I mean. Okay, so I don't require that for all values of mu, but at least so locally mu near the bifurcation point. So what that means that if I plug in that value of mu, then that's going to be the same as minus f minus taken at minus y, right? This is just a definition of being odd. So what I can do then, I can take the second Jacobian of this second derivative, which will be then a 3 tensor, if this is really a vectorial function. And but it doesn't cause any complications for me. I can just, for my purposes, I will not need to work with the coefficients of that. If I take 2 derivatives with respect to y and plug in y equals 0, then this is what I get on the left-hand side. 2 derivatives of y first, and then I set y equals 0 second. Then this is what I get. And then if I do the same on the right-hand side, then I will have to deal with this minus sign twice. So when the first derivation gives me plus here, but the second time it gives you minus again. So after the dust settles and I plug in 0 again, and this is what I get, right? Which is only possible. So this 3 tensor is equal to its negative if, and this is going to be this is how I codify my assumption, is that the second derivative of f at that point, the critical point at the critical value of the bifurcation parameter is 0. Okay, so this is where I wanted to get. So this is my set of assumptions. This is the starting point for this type of bifurcation that we're discussing here. And it turns out that the universal unfolding for this is nothing that would surprise you based on what you have already seen. Let's try to guess that. And then this is what people did and then justified it. This is not too bad at the linear level. It already knows everything I require in this setting. It's a nonlinear term that messes that up, right? And no matter what I do, no matter how I multiply with anything, this is an even term, no matter what. So it will just not arise because it cannot. It would break the symmetry that the system has. If I try to calculate this term on the center manifold, I should get 0 because otherwise I would break the symmetry. So then I take the next one. So what's the next one? Well, it's x cubed, right? And then again, I have the usual plus minus business that comes out from the rescaling. And indeed, that anticipation is correct. So with some one-dimensional unfolding parameter mu tilde, the normal form, the universal unfolding, so the parameterized version of the normal form is that covers all nearby topological equivalence classes is this, where I can immediately factor it out. The x term, it would be plus minus x squared, okay? And x is one-dimensional, and mu tilde is also one-dimensional. Okay. So that's the universal unfolding for this case. What is the bifurcation diagram like? Again, let's take the minus, so because we've already done that. And I'm going to draw the bifurcation diagram, which is again still a one-dimensional system, so I can be ambitious, not just generally bifurcation diagram is in a high-dimensional setting is somehow some attempt to show how the fixed points change as a function of a parameter, right? Then when you have a high-dimensional system, then this line, the cross line in the x direction is insufficient for representing the whole dynamics. But in a one-dimensional case, I might as well paint the whole dynamics on that line. So again, I'll just draw these one-dimensional phase portraits or phase spaces corresponding to that value of mu tilde. I draw a bunch of them, and then we'll just draw in what happens in those. Remember the constraint that the equilibrium point is always a fixed point, and you can, what my argument for the linear stability of that equilibrium point is identical to what I had in the previous example, because I have not changed the linear part from the critical setting. Remember the critical setting was this same linear part. And it's all about what I'm talking about is the stability of the origin, so that the conclusions remain the same. The question is what happens away from the origin. That's the only question here. So at least locally, I can draw the same arrows that here the origin is stable, it starts becoming unstable. And here I don't yet know, right? Because for this I need to write on the axis. It's not that relevant either, because the reason why I'm doing this to begin with, because I don't anticipate being there all the time. And I really want to be familiar with the whole neighborhood of what's happening. But if I'm there and I want to do an honest job in drawing the arrows, then I need to analyze the nonlinear system. So the nonlinear system is now cubic, right? The new nonlinear part, because right at that point mu tilde is 0. So right at that point, when I have mu tilde equals 0, then I have x dot equals minus x cubed, right? So when x is positive, this gives me a negative force. And when x is negative, this gives me a positive force, so to speak, or derivative. So it does switch sign. So in this case, I will have a weak but attraction still. And was already too fast in. No, I actually indicated, but no, this was correct here. Well, it wasn't, because I was talking too much and I was not paying attention to what I was drawing, right? Because I have instability here, so they're pointing away. So here, this jump from this to that, it's never a good thing when you see that the arrows going against each other. But the resolution of that this is really, really very slow decay, and all of a sudden it's sort of at the level of the linear system, it's neutral. Linearization doesn't know about that; it just gives you 0. And then very slowly I start picking up this instability. Okay. But more importantly, when I'm in the negative territory here, all of a sudden I have an additional equilibrium point, because when mu tilde was negative, I could not solve this system for 0. X squared, so minus a negative number minus x squared cannot be 0. But mu tilde is now positive. And I get two solutions by, if I look for mu tilde minus x squared equals 0, then it gives me two solutions. X tilde equals square root mu tilde. Right. So it's like a square root function. We've seen this before. If you do the stability analysis, you also find that these branches are stable. And they come in with a tangent because I just derived the formula for that. I wrote them out. It's disappeared now, but you can reconstruct that. So it's like a fold, except that the two branches in the fold have the same stability type. We've seen this already in a more general setting, not when I was systematically discussing bifurcations. And I already told you that this is called a pitchfork bifurcation. And because it happens over the critical value, definitely this time, we would call it a supercritical pitchfork. And this is what we see a lot in mechanical systems. For the plus sign, it's good subcritical. That doesn't change much, except that you will have it here. Okay. And then, of course, then that will be a red curve then, because me changing this sign doesn't change the conclusion about the linear system. But what I introduce, this part will be red, so that that parabolic shape of fixed points will be formed by unstable fixed points. Okay, and on this side, I will just have a single fixed point, this one. Okay, nothing else. So that's the subcritical version that you can work out. Now, where would this happen? Actually, it may or may ring a bell. So just think about the phenomenological experience that you would have. You're changing a parameter. Let's just say it's in fact growing, right? And nothing changes. And you have an equilibrium at 0, okay? And all of a sudden, that equilibrium loses stability, and you have two competing symmetric equilibria to which you can go, right? Does that ring a bell? This happens a lot. This is the basic phenomenon that you see in buckling. When you push say a structure, or in the simplest case, a beam, for a while, nothing really happens, right? And you reach a critical level and it snaps either way, depending on what perturbation you gave, right? And then if all goes well, it doesn't get destroyed, but it stays in a buckled state. This is indeed the basic bifurcation that's responsible for buckling. But this has, on most buckling models, when you learn about it first time, you learn about the Euler beam, which I also learned about as an undergraduate and completely bought it. I remember at first when I was preparing for an exam, I said, wait a second, this is a linear beam equation. And the professor was showing us that this is a solution. And he said, well, this is also a solution. This is also a solution. And the higher one is also a solution, and said that this explains buckling. How does that explain buckling? It's either this or that, or that. What is the mechanism? So there was no dynamics in those simple static buckling models. This is the dynamics of buckling, right? This is when you start adding, when you consider a partial differential equation that also has a time derivative in it, rather than just a static problem, then this will happen on the one-dimensional center manifold of that partial differential equation for the beam, because luckily all this extends to infinite dimensions as well. So, and that's a partial differential equation has an infinite dimensional flow operator with all the headaches that creates. But this is exactly what will happen on a one-dimensional center manifold that's behind buckling, dynamic buckling, that is. So example in practice. Is buckling. And just to kind of, in terms of a picture, you have a beam, and you're pushing it with force here, and you increase the force, okay, then at some point, and this is what's often forgotten in buckling, that this remains an equilibrium point. This remains a possibility because the system is still completely symmetric, okay? There's no asymmetry. So this is alive and well, this equilibrium, except that you will not see it because there will be imperfections, even in your forcing, or your system gets a perturbation because the slight trembling in your experimental apparatus, right? And you could delay this buckling if you were to create perfect conditions that eliminate the asymmetry. But let's see if my drawing, yeah, it knows that, okay. Wow, this is a bit, you know, but then I have to draw joints here because I have to respect the boundary conditions. Okay, so it will be more like this. And this is what happens then. So this is larger force. And what happens, you snap to one of these positions. And then in turn, those positions are, until any further bifurcation happens, they are stable. So if you push them in either direction, they are stable. Well, that's why you observe them. Otherwise you wouldn't, because my asymmetry argument and little oscillations and imperfections would work equally well. If they were not stable, you wouldn't see them. This is sticking there, right? So they are stable. But this cannot just happen to beams. It can happen, you know, to basic more complicated structures such as shells. So this is very important. And again, it's due to a bifurcation. Just be aware it's due to this pitchfork bifurcation on a one-dimensional center manifold. There's one more left out of these codimension one bifurcations, and it actually even looks more complicated. We are very lucky that it's still codimension one. And it's actually very important too. It's not about adding one more symmetry to the case of a zero eigenvalue, but looking at what the next possible more complicated degeneracy may be that leads to a bifurcation, still the lowest possible order, but what's next in order, rather than adding these idiosyncratic assumptions that, okay, but not only zero eigenvalue, but also, why don't I go for the next case in the hierarchy where my eigenvalue is not zero? But what? So my next complexity level would be that the eigenvalue is still on the imaginary axis of the complex plane, but it's not at zero. So it's an imaginary eigenvalue, but then it will have a complex pair because those come in pairs, right? So the next in complexity would be a pair of purely imaginary eigenvalues at the bifurcation point. And since I'm listing it here, that turns out to be still codimension one. Now, let me tell you that if it was a double zero eigenvalue, then even though I have not left the imaginary axis, I have not even left the 0 point. If I had a double zero eigenvalue, that would already be codimension two. So it's kind of funny, isn't it, that when you actually even leave the eigenvalue and have two purely imaginary eigenvalues, then even though you have two distinct eigenvalues, it's still codimension one. The intuition for that is that these are not independent. They're strongly related to each other, right? So it's not, these are not independently moving possibly two eigenvalues. They're absolutely tied to each other, okay? So that's why one still can have hope that this is codimension one, and that turns out to be correct, that expectation. So, but let's take stock as to what the assumptions are. I start with this, again, n-dimensional system, p-dimensional parameter, okay? And f(0, 0) is still 0, so I have the mu naught, the bifurcation parameter is assumed to be at 0. and f mu naught is 0. But when I now look at the Jacobian of the right-hand side at that point, then my assumption about that is that the center manifold is two-dimensional, but this could still be the double zero eigenvalue, right? Based on this. So I want to clarify that and also add that the nth eigenvalue at mu equals 0, because I think of the eigenvalues as functions of the parameter. That's what they are, right? Otherwise, the eigenvalue would not be the function once I of anything once I have fixed the fixed point there, but it's function of the parameter, and so they move. But what I'm assuming is that right at mu equals mu naught, which is my critical bifurcation parameter, then the nth eigenvalue is just the same as the conjugate of the n plus first eigenvalue, and they are of the form I omega naught, and that's strictly non-zero. So I'm really talking about a complex eigenvalue. So the corresponding diagram in the complex plane for the eigenvalues of the linearization, here's the real part of lambda j, and this is the imaginary part of lambda j, and I may have many eigenvalues all over the place, but some of these might be higher multiplicity and so on. But importantly, along the imaginary axis, which remember is the critical line, the critical set. If you have eigenvalues here, then I have a bifurcation happening right there, most likely. It's not conclusive yet, right? I don't know if things will really bifurcate or not, but this is a necessary condition based on linear analysis, because that's where I lose hyperbolicity for the underlying fixed point. So I have a pair of eigenvalues here, I omega naught minus I omega naught, just that one pair, okay? And this happens typically, I note that here in my notes, that this is sort of the typical loss of stability in oscillatory systems. I'll just say large systems. So that's why it's so, because even in continuum mechanics problems, which in fact, in reality, everything is there's a continuum hypothesis, but everything has lots of degrees of freedom. And as for all we know, infinitely many, right? So typical loss of stability in large oscillatory systems. So the reason why we care about this is not so much because we anticipate a phenomenon like this when I already have a bunch of unstable eigenvalues, which, by the way, would drive me away from the center manifold anyway. So this would be my least concern, what happens on the center manifold. No, the reason why we care about them is that a lot of the engineering structures that are human-made are designed, in fact, to operate in the stable oscillatory regime. So you would have no a priori unstable directions, but rather you would have these eigenvalues hanging out in the safely sort of tucked away from the imaginary axis, kind of in a cloud, sort of, right? But maybe over time your system changes, wear and tear sets in, does happen a lot. That's why people do vibration diagnostics regularly. They try to do it non-intrusively, say even on airplane wings, because the system has a life cycle on it, ages, and there's damage, there's cracks and all that, right? Or simply the operating conditions change. Remember the steam engine example. So what might happen is that you sort of had a pair of eigenvalues that you actually were comfortable with. They were the weakest, but hey, they were, in terms of decay, they were the closest to the imaginary axis, but hey, there always has to be a weakest, right? So that by itself is not a problem, but for some reason, these at some point move out in this direction. And when they do that, you lose stability, and but along one mode typically. The others actually can move in all sorts of different directions. not necessarily in the same direction. Maybe some move in that direction as well, but it's this bifurcation that tends to happen here that is the loss of stability along, and it's usually the lowest mode, right? Lowest means that also the lowest frequency typically. So the others, unlike what I've drawn here, is that this would have a lower frequency, right? In mechanical systems, the others tend to have higher frequencies. So this is all, not only is this the lowest mode, generally speaking, but what really distinguishes it is not so much what its frequency, but it was the weakest damped mode, because the real part of this one was the smallest. See, this is the real part that I'm looking at, and all the others were more safely tucked away. So oscillatory, so typical loss of stability in large oscillatory systems, and I would say along the least damped mode. Okay, that's why it's so important. And now this requires more work, because this means that this assumption, and let's box the assumptions here again. In red. So this also means that the center manifold is now two-dimensional. And let's be actually precise. I'm not just interested in the center manifold at criticality, but I'm interested in the center manifold depending on parameters. So remember this construct that I will be interested in the continuation of this manifold for mu non-zero. And we've seen that that's possible by this trick that we include the parameter as a variable, right? Because strictly speaking, that center manifold is only valid when I'm right here. It's not valid before that, not valid after that. Before that, in the most traditional sense of the word, all I had was just a huge stable manifold for the equilibrium, right? Because I was attracting trajectories from all directions. So the stable manifold had full dimension, same dimension as the system. Here, I now have a two-dimensional center subspace. And once these guys are on the other side, what happens is that I have a two-dimensional, strictly speaking, unstable subspace, and then all the rest form a stable subspace, which is okay, but not terribly helpful, because I'd like to work with an entity that doesn't change its dimension and topology as during this bifurcation, because I want to have the same setting to study this. And that you see here the notion why the center manifold depending on parameters is so helpful, because despite all of what I have just described, it gives me a way to follow a manifold which is the extension of the center manifold in this whole regime, right? In the middle is the center manifold, but it doesn't get destroyed. It still survives as a, generally speaking, a slow manifold, as people call it, because when I'm close, the real part of this eigenvalue is still very close to zero, then I either have very slow growth or very slow decay. Okay, so this is just again recalling the importance of the center manifold depending on parameters. Now I need to recall that because now I want to talk about the reduced dynamics on it, which I would just recall from the, well, first the general form. On the two-dimensional, now it's two-dimensional manifold, which is I still want to talk about the center manifold without the unfolding. To give you an idea, because this is the starting point of the calculation. It turns out that this is pretty much almost everything I need to know. I don't have to follow this manifold. That's the other advantage of the center manifold depending on parameters. I don't have to recompute it each and every time, but it will be sort of a perturbation. The dynamics of it will be the perturbation of what I compute at criticality, at the bifurcation point. So what is that? I will use two coordinates. This is a u dot and v dot on the two-dimensional center manifold. And the linear part will not be a surprise, because this is the standard linear part that you would have for a dynamical system that has a complex pair of eigenvalues, right? You have then complex eigenvectors, but representing the system in the basis of the complex eigenvectors would mean that you're complexifying a real system, which has advantages for proof sometimes, but it doesn't, if you're used to work with complex differential equations, fine. It has computational advantages, but perhaps conceptually, I prefer to stay in the real setting. And then this is what you would have as a Jordan normal form in the real setting, not a diagonal one, because you have plus minus I omega. And they use the same coordinates in which you achieve this normal form to represent the nonlinear terms. So you will have just some sort of f tilde uv and g tilde uv, which are scalar functions. And what the u and v are, they are coordinates with respect to the real basis you have chosen to span the center subspace. So they are coordinates with respect to the basis that you get by taking the real part of the corresponding eigenvector, which is complex En, and taking the imaginary part. Remember, we went through this. So these are both real vectors. So En is a complex vector, eigenvector. Okay. And if you take its real part, that's a real vector. Take its imaginary part, it's again a real vector. And in the original real subspace of the differential equation, the two together, they're not eigenvectors, right? But they together span an eigenspace along which you're circling around, along which you have a center type dynamics. You then use the same coordinates. You pass the same coordinates from your original coordinates, and at least over this happens once you have already restricted the dynamics to the center manifold, right? That's why it's only two-dimensional. So you look for the center manifold as a graph over that particular subspace, and you then calculate the shape of the center manifold and the reduced dynamics on the center manifold, as we have already discussed on simple examples. Now that's only at criticality, but we are interested in doing two things to this system. We're interested in perturbing away from the critical case so that we can track what happens when you have a loss of stability like that. That's one thing we're interested in. And the other thing we're interested in is that simplifying these functions as much as possible for the purposes of analysis. And the tool for that was normal forms, which I flashed for you and did one example, not the general theory, but that comes really handy here. People have done that because they try to knock out as many terms from the nonlinear functions here as possible so that we can still do a qualitative analysis comparable what we were able to do in these simple cases, right? It's not a priori clear that we can do that because these were one-dimensional dynamical systems on which we can do practically everything we want, but not on a two-dimensional coupled set of nonlinear differential equations. So normal forms here come really handy. So this is again a calculation that some of the textbooks do in detail. I only give you the result. So the normal form, now, like I said, we want to do two things. One of them is track the manifold, which is no longer just a center manifold, but it's a center manifold depending on parameters. And it's not even necessarily, it's attached to another fixed point. In my notes, I refer it to as the zero, so you can shift the coordinates if you want, and then it will become zero. That's why I refer to that. But in fact, generally speaking, that fixed point might move. I have not mandated in my setup that zero remains an equilibrium point, but you can just, if it moves, then you just redefine your coordinate system and always move with it. So that's not our problem to shift zero, the equilibrium point to zero. And this would be again, this is the, what was the parameter dependent center manifold. Okay, so this is something that I cannot do here, but it's not, it's an interesting calculation. And it involves actually the type of considerations I sketched for you in the one-dimensional case. What's the idea? Let's experiment with near identity transformations that are identity plus some polynomial terms. And at each and every order, let's try to select those polynomial terms that in the transform dynamics, I'm knocking out as many polynomial terms from here as possible. I'm decimating the right-hand side for the purposes of simplifying the qualitative analysis of the system. In the little example that we did, I had something already in mind, and I was able to successively knock out everybody else, okay? This is an example in which that's not the case, because you try to do it, you do the same approach, and you just find at some point that no matter what I do, I cannot knock out this term. The no matter what I do, I cannot knock out this term happens when that equation that you're trying to solve for that coefficient to be 0 is not solvable. So it's a linear equation always, but it doesn't have a solution, right? So some sort of degeneracy occurs that prevents you from solving that homogeneous linear equation, okay, inhomogeneous one, and the inhomogeneous term is not in the range of the linear operator on the left-hand side. So you cannot solve it, right? So that it turns out it's due to, but it's not this phenomenon, an unremovability of a term is called a resonance. So that means that nonlinear term, I mentioned that when we were discussing the normal forms, is that's just essential. It somehow carries essential physics, essential nonlinearity. The rest is basically related to your choice of coordinates. If you deform a coordinate system, you can get rid of them, but not these, all right? And these are then related to non-solvability of these linear equations that arise successively when you try to knock the terms out, okay? And in this case, instead of writing now the equations, say again in U and V form, Cartesian forms, it turns out to be advantageous actually to introduce polar coordinates as well for the normal form and write the normal form in polar coordinates because it's easier to analyze. So in polar coordinates, that normal form looks like this, r times r, and there will be some constant which depends on your mu, that parameter, that the one-dimensional parameter that we are introducing to unfold the bifurcation, plus there will be some other coefficient here, which again depends on that mu, and that multiplies r squared. And there will be higher order terms. And you can go on and on in this normal form. And the pattern that kind of, let me write out the full normal form, because this is just the r variable, but like I said, let's use polar coordinates. So the theta dot equation is omega nu tilde plus e nu tilde r squared plus order r to the fourth. The distinction between nu tilde and nu, remember, was that nu tilde is now a one-dimensional unfolding parameter. That might just be one component of your original mu, or in a lot of the problems, excuse me, you just define mu to be one-dimensional to begin with. So it may be mu, maybe it's just combined a few things, but something that gets you from one side of this proverbial bifurcation surface, right? You're here to the other. Because it's just one surface, because I'm telling you that it's codimension one, okay? And that requires work to prove, but that work has been done, okay? The thing about this normal form, this is a linear term, okay? This is basically a linear in R in the distance, and this is just rotation. So the linear dynamics is encoded here. And the next term, you would expect two things. Well, why aren't these coupled? You know, I could have r times sine theta or r squared sine 2 theta, these terms. And you would, in fact, if I had changed to polar coordinates here, I would have those terms. But what the normal form does, it nicely cleans things up and removes the coupling between the two equations. So note that there's no linear term within this factor linear in R. So you just have the linear term here in the R equation, and the next one is cubic. We see that we have seen that in the pitchfork bifurcation case, but that was the result of me prescribing symmetries. This, I'm not prescribing any symmetry here, and yet I have that here, that the next term is cubic. So this is a particular feature of this type of bifurcation that we'll be describing here. But anything that was in between, within this, I could have, I could have a linear term in R that would be quadratic for the full equation. I can remove that. Also note that I can also remove the quartic parts because the next one is order R to the 5. And if I did not remove those, but just switch to polar coordinates from this equation, then those would be actually coupled to the theta equation. But these normal form terms, the resonant terms, so to speak, the change are nice in this respect that they make the two equations decouple from each other. Because the R dynamics now is independent of the theta dynamics. The theta dynamics is a rotation. It's not independent, but consequential with respect to the R dynamics. If I understand the evolution of R here, I can use that evolution, plug it in here, and then I get the theta evolution, right? But when R is small and close to the origin, I just get a rotation here. Now, when I add all the high order terms and I stop the normalization at some point, then there will be coupling between the two equations. And then, I leave those terms unnormalized, and they will be depending on both of these variables. But up until the order that I carry out the normalization, this clean decoupling luckily remains. So that's very helpful. So I just want to say what these are. So the d mu tilde actually turns out to be related. If you think about it, this is kind of expected. That's actually just the real part of that nth eigenvalue, okay? And the omega mu tilde is just the imaginary part. Of that eigenvalue. So these two terms here, I would get these already if I simply kept the, I would add the mu, the perturbation, I would add the unfolding to the system, but I only kept the linear part, right? Then I would actually, in this form, I would have then d mu tilde here appearing in the standard Jordan form, and I would have omega mu tilde appearing there, minus, and then here plus, so the same thing, and then I would again have d mu tilde appearing here. So what I would have here, or will have appearing here, when I actually perturb from criticality and move, the real parts appear here. It's the same real part, and the imaginary part, as it would move as a function of mu, appears here. But that's just the linear damped dynamics now, right? At mu tilde equals 0, I have a center, and then this tells me whether this is positive, then I have growing oscillations, like so in the center manifold, and at linear order. And if it's negative, then I have decaying oscillation. Okay, but that's not the end of the story because I have these nonlinear terms here. And whereas I can get these from a linear analysis, I cannot get these from a linear analysis because these are part of the nonlinearities. Okay, so this was actually work to determine these, but the formulas are generally available. And it turns out you don't need the whole functions as a function of mu tilde, but you can, or it's already enough if you know what they are at mu tilde equals 0, okay? Which means that the nonlinearity of this system in polar coordinates is already enough. So you don't need to, start changing this system away from the bifurcation, because for what's coming, it's enough to know the value of these at mu tilde equals 0. And those have been computed, and I will just introduce them, part of them as a definition. And I have them in my master set of notes here. So if you excuse me, I just copy these because it saves some time for myself writing. And because I copy these, I have to clean that up then afterwards once I have pasted them in here. Oh, I didn't copy anything. So let me try again. So what did I do wrong? Screenshot. Yeah, it's a new function. Yeah, and then it goes into copy then. So it's a bit more complicated than it used to be. And now it appeared. And let me work on this a little bit to explain what this is. So first of all, let's spend some time and seeing how much of this is important for later. And it turns out that only the leading order term of this in mu is enough, because I'm going to be close to the bifurcation value in mu, so I'm just going to keep the leading order term in this in leading order one with respect to mu. Okay, it doesn't have any constant term with respect to mu when I Taylor expand it, because it's 0 when mu tilde is 0, right? Because the real part then is 0. So to get the first non-trivial term and the Taylor expansion of this function, I need to differentiate with respect to mu tilde. But don't forget that this function is just the real part of the critical eigenvalue that's crossing over here. So if I know this eigenvalue is a function of mu tilde, which is a linear analysis fundamentally, then I can just take the mu derivative of that eigenvalue. I have the tilde off here, okay? And that will define me the leading order term coefficient here, d naught. And with that, the help of that, I will approximate this as d naught times mu tilde. And I imagine here that I'm basically adding the order mu tilde squared terms here, okay? So I'm just keeping from everything the leading order approximation. That turns out to be enough. In the same spirit, I have the imaginary part right here, which is a complicated function of mu tilde. Why don't I just keep the leading order term? Now, unlike the real part, the imaginary part does have a nice non-zero limit when mu tilde is 0. What is that? Well, it's just this frequency, right? That's the leading order term, because at mu tilde equals 0, I'm on the imaginary axis. So that's a kind of a no-brainer calculation. I don't need to take a derivative there. I just take its value at 0. Oh, sorry, I'm pointing at the wrong thing. Take its value at 0. So I take the eigenvalue that's crossing right at 0 where it's crossing. And that's, I just call that omega naught. So here, my approximation for this term will be omega naught, okay? Plus, I imagine that the rest, the mu tilde squared terms will be tucked away in the higher order terms. Once again, that omega naught is just what omega naught was here, the distance from 0, okay? Now, for me it's a good thing that the R dynamics decouples, because that's what describes evolution, in and out evolution on the center manifold. Distances, the rotation is good to be aware of, but that's not making any difference in terms of stability, right? So my focus would be fundamentally to get a hold of the leading order terms in this equation. So the next one on the list is this term. Now, this is a truly nonlinear term in general. But again, I'm hoping that the leading order part of it already tells me what the story is, and that expectation turns out to be justified. But that leading order term is nothing else but the normal form of this system, the nonlinear term in the normal form of this system, the system at criticality, which depends on these nonlinearities, okay? Now what I need to do, I need to reduce the system to a two-dimensional center manifold. This is the reduction. And then I need to bring it to normal form to get this coefficient. This calculation has generally been done. I myself did it once as an exercise because I needed it for something else. I wanted to make sure the coefficients are correct, and I needed it in complex form. It's a very instructive exercise. It's algebra, but one that really understands how normal form works. Specifically, one can express how this at mu tilde equals 0 depends on the coefficients of the polynomial expansion of these. And this is what I'm writing out here, that if you have the standard unnormalized form, real form, on the 2D center manifold at criticality, so you don't have to bother following it away from criticality, those when you know the coefficients in the Taylor expansion, those enable you to calculate this. And this is a universal formula. And this was a celebrated formula that was derived by various authors. The history of it, as I understand, as I heard from one of my professors who was doing his PhD back in the Soviet Union, and he was shown that this was a military secret at some point in the early 1900s or 1920s, because it was so important, it turns out, because this bifurcation just happens a lot in large systems that leave, that lose their stability, and they tend to be oscillatory systems. So think, airplanes, missiles, submarines, whatnot, right? And the minute you think about those, if somebody figures this out, that they have a reason to keep it secret. And that's how it worked back then. So it was, in some archive, this was still classified as secret, right? It's no longer a secret, but back then it was. And I think it was due to then, if I'm not mistaken, Andronov, who was a Russian mathematician, Soviet at the time, right? So it's basically a function that contains the cubic coefficients of both that you get. So these are basically Taylor expand U and V at UV equals 0. And a coefficient like this would be multiplying the U to the cube power, right? So F tilde UUU would be the coefficient that you find in the Taylor expansion here, multiplying U cubed. Similarly, UVV refers to the fact, well, except that that's not how I've written out. What I'm saying is related, except that there's the factorial in the Taylor expansion that I would not recover. So let's actually just define them in terms of these derivatives. So let's just say that these are partial derivatives. So which are not the same as the Taylor coefficients, because those would have the factorials in there, right? They're related, but they're not the same. So just think of these as the third partial with respect to U of the first function, the mixed partial UVV of the first one, then the second one you do UUV, and then you do VVV, and then you plug in UV equals 0. 0, 0. Okay, so these are then partial derivatives. And this is just for the purposes of what I'm saying. This is not important. So I tried these out, but right now, sorry. It's a bit confusing. So what I'm doing is using white because I can't erase these given that I copied them in. So the whole thing is treated as a picture. So I have to put white on it to get rid of them. All right. So I did that to some extent. Okay, those are just other comments. So basically these are then the partial derivatives. So the subscripts refer to partial derivatives. So the structure of this coefficient, so remember there's a lot of information just going into this one coefficient because you're constructing a whole transformation that knocks out all the other terms and just preserves what's important about your nonlinear system in this single nonlinear coefficient at cubic order. So it will depend on all these other original cubic coefficients, but not only on those, you then also have a bunch of second order coefficients. So these are second order partial derivatives that come from the quadratic terms, that is lower order terms of these, but then products of those will arrive. And again, you evaluate them at 0. This is multiplied by 1/16, and this is multiplied by 1/16 omegas. And then I think there's a knot missing here because that's the I. So long story short, it's enough to know what your system at the bifurcation point gives you this information because that's the imaginary value, imaginary part of your eigenvalue there. This is also just about the system at the bifurcation point. You don't need to unfold it because these are all functions that you computed at at that point. The only sort of non-trivial information that relates to the family, because it somehow describes the crossing of the eigenvalue through the imaginary axis, is this one. But this is doable through a linear analysis. You don't need to track the non-linearities. You just basically focus on the linear part, focus on this picture just here. And essentially what then Denon describes is the speed at which you're crossing the imaginary axis, right? Because the larger this derivative is with respect to mu, the faster you're crossing. So this is somehow your speed at which you're crossing. And this is the essential nonlinearity that you have inherited from this system. There are similar calculations for these, but they're not that important. At leading order, we know what this is, and I'm going to be using that here. So this is very much computable without actually the formula is given to you, and in a given application, therefore, you don't have to do any kind of nonlinear analysis because people have done it for you in general. So with this one, we get a theorem with these ingredients that I have just enough time to state, I think. And then I show you some applications next time, just tomorrow. And in this more general form, this is due to Hopf, which is a German mathematician, if I remember correctly, and Bogdanov. But as I told you, I mean, some Poincaré was already looking at this, and apparently, for the case of just a two-dimensional system without center manifold reduction, so you already assuming that you just have two dimensions, nothing else, that's your phase space. You don't have to reduce the center manifold. That was the one that was already known in the Soviet Union, and that name was Andronov, who cleaned up the 2D case, which is n equals 2. So your whole phase space is the center subspace at the critical level. Okay, so this theorem is pretty powerful because it enables you to make predictions. So you have to make some assumptions, but those are non-degeneracy assumptions. Basically, that these parameters are non-degenerate for the purposes that you calculated them. The first one being is that the speed at which you're crossing the imaginary axis is actually non-zero. Very important, right? So remember, this was the speed at which you're crossing. And if that speed is zero, then what that pretty much means most often is that instead of doing this, you're doing that. And that's not a good thing, because then that means that you're unfolding the parameter that you have chosen to unfold your system is not working well. You're turning back from the bifurcation surface. This is not the bifurcation surface. That was a different notion, but the turning back would manifest itself in exactly the same way as it does in the space of dynamical systems. So here it's not the dynamical system that does this, but it's the eigenvalue that does that. But it translates to the dynamical system doing this. Where was that? Right? Because you're just basically touching the bifurcation surface, but you're not getting on the other side. So this condition prevents that from happening. You really are crossing through from one equivalence class to the other. So therefore, well, the meaning is that lambda n and lambda n bar equals lambda n minus 1 do cross the imaginary axis of the complex plane. Okay, so that's very important. So that's a non-degeneracy assumption that your parameter that you picked is indeed a good unfolding parameter. And the other non-degeneracy assumption would be is that, hey, you do actually have a nonlinear system. Because what if I just repeat this for a linear system? I'm not going to get any bifurcation. A linear system cannot double its equilibrium point. I want to have a nonlinear phenomenon. I want to have a non-zero coefficient here. Because if it's zero, then with all this leading order analysis argument that I have, with all that work, I'm still just getting a linear system. So the next one also makes sense, which is thus A naught is really non-zero. So that means that the leading order nonlinearity is in R is non-zero. And I just wanted to know that this is not satisfied for one class of systems for which this is not satisfied is linear systems. And if that was the only class, then I probably wouldn't even mention, but to be very much aware that there's actually another class of systems for which this is not satisfied. If your underlying system before you added the bifurcation parameter was conservative, or in more general terms, Hamiltonian, or even reversible, so it had some of these conservative types of symmetries, then interestingly, this is also zero. So one then has to employ other tools. So it's not true for conservative systems either. If you know what Hamiltonian systems are, then you know what this is. If not, I recommend part 2 of this course. It's a very broad framework formulation to describe conservative systems, so to speak. Okay. Let me give you an example. Suppose you have a pendulum, something, and you just add linear damping, then that term there would be zero for the pendulum if you were to calculate that. Well, it's just that the pendulum doesn't have a center manifold. But so what has is some nonlinear oscillator, which is conservative. Okay, if you did this analysis for nonlinear, say, Duffing equation, which is conservative, and you added linear damping and nothing else, then that term would actually be zero. And this calculation would not be conclusive. So, for instance, x double dot plus x cubed. If this was your, let's use y because that was my y double dot plus y dot. And you know, as also add the unfolding. Now let's add the unfolding. So plus, so this is y double dot plus mu tilde y dot. So that adds the damping plus y cubed equals 0. For this one, the damping brings in the non-conservative effect, but the rest is conservative. It conserves the energy. And for that one, this one turns out to be 0. In this case, the dimension of the center manifold at mu tilde equals 0 is the same as the dimension of the phase space. It's the same as n, right? You could do this analysis in that case. Sorry, I'm going over time and I have to leave anyway. So I'll just stop here. If you have any quick questions, I'll take them. I have not stated the theorem, but at least cleaned up the assumptions, what they are. And then there will be a statement. And the statement is that the leading order part actually captures the full dynamics. And then we'll just explore what happens in the leading order part. And some really interesting things happen already on there, because it's now a two-dimensional case. Any quick questions?
I have a question.
Yeah, please.
So is there a relation between the dimension of the central manifold and the codimension?
The dimension of the center manifold and the codimension of the bifurcation. That's a good question. I don't know of a general relationship like that. Here, there's certainly no one-to-one relationship because the center manifold here is two-dimensional and the codimension of the bifurcation is 1. Right? In the previous case, there was a one-to-one relationship. Generally speaking, I would say there's an intuitive relationship between the number of independent eigenvalues spanning the center manifold, the center subspace. And generally speaking, it is true in the absence of other symmetries that the number of parameters that you need to unfold the bifurcation is the number of independent eigenvalues that just are not tied to each other. If you have, like I said, a double zero and you have no reason to keep having double zero, so you have no other symmetry, then generally speaking, that's a codimensional one bifurcation. If you have two pairs of complex eigenvectors, which, remember, each has its own two-dimensional invariant subspace, and you have two of them without resonance, that's already a four-dimensional center manifold, but that turns out to be a codimension 2 bifurcation. Guggenheimer and Holmes describes that. Why codimension 2? Because you have one pair of eigenvalues connected to each other, okay, the one, and you have another one. So again, your degrees of freedom, so to speak, right, is 2.
Mm-hmm.
And likewise, if you had two pairs of complex eigenvalues that are not tied to each other through a particular symmetry, but otherwise independent, and you had then a simple 0 on top of that, again, then that would be a codimension 3. So that would be the intuition. But that's already a 5-dimensional center manifold then.
Okay, thank you.
You're welcome. Anybody else? Okay, looks like we're done for today. Then see you tomorrow, and then we'll get more into this. And this bifurcation is named after, actually, in the end, Hopf. So this will be the Hopf bifurcation. Very, very important one. I'll show you some applications. Have a good evening.